At Hamelin Pool on the western coast of Australia, the rocks in the water are alive. Bacteria and sand build them one layer at a time, in much the same way as the oldest fossils on Earth, 3.5 billion years ago. A stromatolite is a layered sedimentary mound, built slowly by a community of microbes. The community is almost always dominated by cyanobacteria, single-celled photosynthesizers that release oxygen as a byproduct of their metabolism. The bacteria live as a mat on the stromatolite's upper surface. They secrete a sticky biofilm. The biofilm traps sand and carbonate grains settling from the water above. Each year, a thin layer accretes, the living mat migrates upward, and the old layer beneath it hardens into rock. Hamelin Pool sits at the southern end of Shark Bay, a large inlet on the Indian Ocean coast of Western Australia. Shark Bay became a UNESCO World Heritage Site in 1991, in part because of the stromatolites. The pool itself is hypersaline, about 1.5 to 2 times the salinity of normal seawater. That salinity keeps out the mollusks and fish that would, elsewhere, graze the bacterial mats away. In the refuge it creates, pillars of stromatolite up to 1.5 meters tall, about 5 feet, sit in shallow water at low tide. They grow at roughly 0.5 millimetre a year. The mechanism is slow and unglamorous. A square centimetre of cyanobacterial mat contains millions of cells. Each cell performs photosynthesis, takes in sunlight, splits water, releases oxygen, fixes carbon. The collective effect, over a year, is to build up calcium carbonate among the sand grains and bind them into a millimetre-thick lamina. The mat then moves upward, chasing the light, the lamina below it cements, another millimetre accretes. A pillar 1.5 meters tall has been growing like this for something on the order of 3,000 years. Stromatolites of this kind were first identified at Hamelin Pool in 1956. Before that date, they were known from the fossil record alone. The same pattern, running in the same way, is the earliest strong evidence we have of life on Earth. In 2006, Abigail Allwood and her colleagues published a Nature letter describing a stromatolite reef preserved in the Strelley Pool Chert, a rock formation in the Pilbara Craton of Western Australia. The letter identified 7 distinct stromatolite morphotypes: cones, small domes, flat layered sheets, and others, preserved together in what had once been a shallow reef. The reef is 3.43 billion years old. Before the letter, earlier reports had called the structures possibly biological. Allwood's detailed reef-scale analysis, matching the morphotypes to known microbial mat behaviors, moved them from possibly to firmly biological. What cyanobacteria did to the planet is the reason the rest of this matters. For roughly the first half of Earth's history, the atmosphere contained almost no free oxygen. Cyanobacteria had been photosynthesizing for hundreds of millions of years before their waste product began to accumulate. The ocean and the weathered rock surface absorbed it first. Around 2.4 billion years ago, those sinks saturated, and free oxygen began to build up in the atmosphere. Geologists call this the Great Oxidation Event. Every animal, plant, and fungus that has ever existed depends on that oxygen. It came from microbial mats, building layer by layer, for the better part of 2 billion years. Living stromatolites should, by rights, be everywhere. They are not. Around 540 million years ago, in the Cambrian explosion, the first grazing animals evolved, mollusks, worms, and the ancestors of crustaceans, and began to eat the bacterial mats wherever they could reach them. From that point on, stromatolites disappeared from normal marine environments. The few places where they still grow are places grazing animals cannot tolerate. Hamelin Pool is one, where the water is too salty. The Exuma Keys in the Bahamas are another, where tidal currents keep grazers moving. Lagoa Salgada in Brazil is a third, a coastal salt pan. Each is an exception. The rule, for 400 million years, has been that stromatolites no longer form. Abigail Allwood, the first author on the 2006 letter, completed that paper as part of her PhD at Macquarie University, under Malcolm Walter. She now works at NASA's Jet Propulsion Laboratory in California as the principal investigator of PIXL, the planetary instrument for X-ray lithochemistry, an X-ray spectrometer mounted on the turret of the Perseverance rover's robotic arm. PIXL's job is to look for the kind of small-scale chemical and textural patterns that distinguish biological layers from purely mineral ones. Perseverance is working in Jezero Crater on Mars, an ancient lake basin. If stromatolite-like structures exist there, Allwood's instrument can find them. She is the first woman, and the first Australian, to serve as principal investigator on a NASA Mars mission. The stromatolites at Hamelin Pool are, in every way that matters, the same kind of reef that once built Earth's atmosphere. They have been building it in one form or another for 3.5 billion years. They are still here.